Okay. All right. Everybody's here. Yeah. Let me see if I can remember some names really quick. So I know Ben, Jasmine, Tavoy is online. Let's see. You are Nathan. You are Chize. Did I say that right? Chize. You are, I don't remember. What's your name?
Richard.
Richard Simon. Richard Simon. And you are?
One
Jung. Okay. All right. Did we lose somebody? Have we already had one casualty?
Yeah.
Other master student bailed. That's fine. I didn't think he. I'm not sure he knew what class this was, so that's fine. Okay. Any questions then before we get started? So today is going to be the first, I guess, full lecture we will have, and we'll just pick up where we left off last time with the Solow growth model. And Tavoy, chime in if you have any questions along the way. Okay. So I think where we left off last time was we looked at Euler's theorem, right? So we introduced the neoclassical production function. And what were the properties of a neoclassical production function? That the marginal product of capital and labor was both positive. The slope of the production function was positive. The second derivatives were negative. In other words, it's concave. So the production function exhibits diminishing returns to capital and labor. And then also a very important property was that it was linearly homogeneous. It had constant returns to scale, right? And one of the implications of linear homogeneity is that the production function satisfies this thing called Euler's theorem. And we proved the two basic features or properties of Euler's theorem. We'll use that again today in our discussion. Let me briefly mention the second critical assumption of the neoclassical production function. And that's what is termed the Anata Conditions. Now that may sound really complicated, but it's not. It just tells us something about the shape of the production function at extreme points, okay? Essentially what it says is that in the limit, as capital goes to 0, the marginal product of capital is going to equal infinity. And in the limit, as capital goes to infinity, the marginal product of capital goes to 0, okay? In other words, it says that the slope of the production function with respect to the capital stock is really steep for small levels of capital and basically perfectly flat for large levels of capital, okay? There are other Anata conditions that correspond to this for labor, and you can read those in the lecture notes, right? It's the limit as L goes to 0 of the marginal product of labor, so F sub L is also equal to infinity. And the marginal product of labor goes to 0 as labor goes to infinity. So the slope of the production function is super steep for low levels of inputs as K and L get close to 0. And it's essentially flat as those inputs become abundant, regardless of the particular value of technology. That's what the Anata conditions state. And there's one more minor feature of the Anata conditions, and it is that I need to use a marker that actually works. That is going to help. And it is that the capital stock is what's known as an essential component of production. In other words, it doesn't matter if we have a ton of labor and a lot of technology. If you have 0 capital, you're going to produce 0 output. So at some level, there is kind of perfect complementarity between capital and labor, right? You got to have some capital in order to be able to produce any output, regardless of how much labor or technology you actually have. So capital is an essential input into production. Now, this may not be clear at this point, but the role of the Anata conditions, I think, will become more clear when we try to establish the existence and the uniqueness of an interior steady state solution to the model, okay? in particular the existence of rather than the uniqueness, right? In other words, when capital and labor are really productive at low levels of capital and labor, but become less and less productive at large values of capital and labor, that's going to ensure that the model exhibits an interior, long-run, steady-state solution. So those Anata conditions are actually critical to proving that property. Okay, now assumption one is useful, is extremely useful in the analysis of the Solow model, because it allows us to transform the model into its per capita or intensive form. How many of you guys in the study of economics have heard of the difference between extensive form versus intensive form? A lot of times it's discussed in context with the labor market, right? When we look at, for instance, the aggregate supply of labor hours, that's the product of two things, right? It's the number of people who are working in times the number of hours that each of those individuals works. That's total labor supply in the economy, right? Well, total labor supply can move around for two reasons, right? Either the number of people working in changes, or the number of hours that each person works changes. That's the difference between the extensive and the intensive margin of labor adjustment, okay? Now, I digress there because it's important in order to be able to solve analytically the Solow model, to be able to transform the model variables into their intensive or per worker form. So in other words, we don't want to talk about the aggregate capital stock or the aggregate level of output. What we want to do is transform the model into capital per worker and output per worker, okay? Now, these aren't the variables that we're necessarily directly interested in, okay? Ultimately, we want to use the model to talk about capital and output at the aggregate level, but transforming these variables is important because it allows us to come up with analytical solutions. The Solow model, it turns out, these aggregate variables are non-stationary. They tend to grow over time. As technology advances, as population increases, capital and output are also going to increase. It's very difficult to solve non-stationary models. We want our variables to be mean reverting. So what we do is we normalize those variables by a growth factor, that is the population. And we can do this kind of stationary inducing transformation. That's what we call the intensive form, okay? And it's very straightforward to do. Let me define a couple of these variables first. Lowercase k is going to be defined as capital per worker. Lowercase y is going to be defined as the economy's output per worker. Richard, you have a question?
When you're talking about stationarity,
Yes.
that means you're talking about like it takes into account for seasonality, correct?
It takes into account what again?
For seasonality.
I can't understand.
Seasonality.
Those seasonality factors are not in the Solow model. Okay. Those are factors that influence these high frequency time series models. That's not what I'm talking about. I'm talking about, so there are long run trend components in this model attributed to growth in the population and growth in technology. So all the variables in the model are going to tend to rise over time, okay? We want these variables to be we want them to be stationary or mean reverting. Well, we've got to do this kind of transformation, okay? I think you'll see that once we work through the model.
Just real quick, that little KT, I was reading the Solow paper. Is that little r in the Solow paper? I think he referred to that as well.
Oh, I don't remember. It's been so long since I looked at it. We're going to call in this class lowercase k is capital per worker. And in fact, a lot of the applications we'll just assume constant population. And so there's really not going to be much of a distinction between aggregate and per capita capital. But these are going to be the variables of interest right now. Tavoy, I'm sorry about changing the ink here. I'm trying to find a marker that will show up well on the board. So just bear
That's
with
okay, sir. I can see it.
Okay. All right. So the fact that the production function has constant returns to scale enables us to transform the production function into its per worker form. All right. How do we do that? Let me set lambda, this scalar that we multiply through the production function, equal to 1 over LT. So this is the trick we're going to employ. Okay. If lambda is 1 over LT, then let's multiply both capital and labor by that factor. So F of 1 over LT KT, 1 over LT times LT, and AT. What is that going to be equal to, given the fact that the production function is linearly homogeneous? If we multiply K and L by a constant factor, lambda, we should end up multiplying the production function by that same constant. All right, so that's going to be equal to 1 over LT, F of KT, LT, AT. And that follows because the production function has constant returns to scale. Well, what is 1 over L times F equal to? That's just YT over LT, right? And what is YT over LT equal to? That's just output per worker. So the production function evaluated at K over L, L over L, and A is equal to output per worker, right? So this is F of KT over LT. What's LT over LT? That's just 1, and AT is equal to output per worker. That means we can write this as F of little kt, 1, and A as output per worker. Now I'm going to make an assumption here, okay? Let me just, for the time being, I'm going to assume that technology is constant. It doesn't change, all right? That's the way I'm going to proceed in the presentation of the basic Solow model. The questions that are on your review, the problems that are on your review questions will generalize this and allow for growth in A. But the mathematics stays roughly the same. We're just going to do this for simplicity in the class, okay? So what do we have here? We have that output per worker is basically just a function of the capital stock per worker. So that implies then that we can write output per worker solely as a function of the level of capital per worker, which I'll denote with a lowercase f to distinguish it from uppercase F. So with constant returns to scale in production, that allows us to transform the neoclassical production function into this per worker form and allows us to consider the level of output per worker in the economy only as a function of the level of capital per worker. As long as we know what little k is, we can trace the history of little y. Okay. Let me use the same logic here to transform the marginal products into their intensive form. And for this, I'm going to drop the time subscripts because they don't really matter for right now, okay? What if we were to take the marginal product of capital and we were to multiply the first two arguments by this scalar, 1 over L? What would we get? The production function is linearly homogeneous. What degree of homogeneity is the marginal product of capital then? The production function is homogeneous degree 1, f sub k is homogeneous of degree 0 by Euler's theorem, right, to avoid 0. And so this should be equal to what? 1 over L raised to the 0 power times f sub k, k, L, A. So if we normalize properly, we get the marginal product of capital evaluated at capital per worker, 1 and A is equal to, what's 1 over L to the 0? Just 1, and that's just F sub K, K, L, and A. In other words, the marginal product of capital at the aggregate level is simply equal to, what's the left-hand side here? It's just the slope of the per worker production function. That's important. In a competitive environment, what do we know about the marginal product of capital? If factor markets are competitive, the marginal product of capital should be equal to the real rental payments on capital, right? And so what this says then is that we can determine what the real rental rate on capital is simply with knowledge of the level of capital per worker. It's just the slope of the per worker production function. This is the rental rate. Sometimes it's referred to as R, capital R. What about the returns to labor or the real wage? Can we write the real wage as a function of just capital per worker? Well, let's apply Euler's theorem. What does Euler's theorem say that F should be equal to? Marginal product of capital times K plus the marginal product of labor times L, right? Production function is homogeneous of degree 1. And this is what Euler's theorem should say. In other words, total output is divided between the returns to capital and the returns to labor in this economy. Well, let me solve this thing for the marginal product of labor. It should be equal to 1 over L times F minus 1 over L F sub K times K. And what is 1 over L times F? We already established that over here, but that's just F of little k. 1 over L times K is capital per worker. F sub K, that's the marginal product of capital, we established up here is simply equal to the slope of the per worker production function. So at the aggregate level, the marginal product of labor is just equal to output per worker minus capital per worker times F prime. Well, the marginal product of labor, of course, is just the real wage. So in the Solow model, we can track the history of the real wage over time with knowledge of the production function and the level of capital per worker. Hopefully you kind of see where we're going with this. The key variable that we're going to try to model the dynamics of over time is what's driving growth in the Solow model is capital per worker, right? The factor payments can be expressed completely as a function of little k. We already know that output can be expressed as a function of little k. So if we can characterize the law of motion for capital per worker, we can back out the implied values for the factor payments as well as output. One last comment I want to make about this intensive form. It also applies to the Anata conditions. Okay? The limit as aggregate capital goes to 0, for instance, of the marginal product of capital should be equal to the limit as capital goes to 0 The marginal product of capital, we already established, is just the slope of the per worker production function. So that's F prime K over L. Well, that's the same as the limit as little k goes to 0 of F prime of little k. The Anata condition says that this limit is equal to what? 0. So the Anata condition holds in intensive form. The slope of the per worker production function is, that's not right, it should be infinity, right? Is infinity as capital per worker goes to 0, right? What happens as capital per worker goes to infinity? The slope of the per worker production function goes to 0, right? So these are not, the point I'm trying to make here is that these Anata conditions hold not just for the aggregate production function, that is the marginal products, but they also hold for the slopes of the per worker production function. So normalizing the production function to make it in intensive form has straightforward implications for the marginal products as well as the Anata condition. Okay, any questions so far about that? I'm actually writing a lot larger than I normally do. Every class I've had up until this point has always complained that I write really small. But now that I'm videotaping it, it looks like I'm gonna have to write bigger. So that means more erasing. So bear with me.
Looks good from the back.
What?
It looks good from the back.
Looks good from the back, okay. I think I would ideally like to be in one of those rooms that has boards like all the way around, and I'm just gonna start here and work my way like around the room. And maybe then I won't have to erase anything by the end of the class. But the students will need swivel chairs that go 360 degrees. All right, Tavoy, I'm gonna move you back over here. This is so low tech, I'm embarrassed. Okay. All right. Let's talk about dynamics of the Solow model. Okay. Because labor and technology in the Solow model grow at exogenous rates, labor grows at the rate N, that's an input, right? Technology, we assume, grows at the rate G, which, by the way, I'm temporarily assuming G is 0, right? What that means then is that if we want to identify the growth path of output or per capita output in the long run, the variable that we're going to be focused on is capital per worker. That's the input into production that evolves endogenously over time, okay? That leads us to a description of something that your textbook author calls the fundamental law of motion for the capital stock, okay? Let's derive what that is. It's very straightforward to do, okay? The law of motion for capital can be derived by simply plugging together 3 things. The evolution of the capital stock, along with the distribution rule for consumption versus investment, as well as the neoclassical production function. Let's start with the evolution of capital. We know from the last class that changes in the capital stock between periods t and t plus 1 are going to be equal to the sum of 2 things. Investment, that's what causes the capital stock to rise, and depreciation, that's what causes the capital stock to fall. So the capital stock will rise between t and t plus 1 if investment exceeds depreciation, or depreciation occurs at a constant rate. all right? How much is invested in the Solow model? Remember one of the assumptions we made in the last class about the behavior of agents in this economy, that they save and invest a constant fraction of their output every period. So it's S times YT, where S is this constant fraction minus delta KT. Well, let's go one step further. What do we know YT is equal to? It's simply equal to this neoclassical production function. Therefore, KT plus 1 is just equal to S F of KT, let's see, plus 1 minus delta KT. This is a nonlinear difference equation that characterizes the law of motion for the aggregate capital stock. But you'll notice here, there's a couple of other variables in here that complicate the analysis. That is labor supply as well as technology. We're going to make two assumptions. Technology is just some constant A forever that we can basically ignore in the analysis, okay? And the other is that labor grows at a constant rate. So what we need to do then is transform this law of motion for capital into intensive form like we just did a minute ago, okay? So how can we do that? Well, what you want to do is you want to divide both sides of the equation by LT, okay? So let's see, we've got KT plus 1 over LT is equal to S times, what's F of KLA divided by L? I can skip some algebra here, right? Isn't that just F of little kt, right? Didn't we just do that exercise a minute ago? So that's S F of kt over LT plus 1 minus delta kt over LT. Okay, so the right-hand side is straightforward. It's just S times F of capital per worker, little k, plus 1 minus delta times capital per worker. It's the left-hand side that's a little odd. What is KT plus 1 divided by LT? Can we somehow transform that into intensive form? Because KT plus 1 over LT is not the same as little kt plus 1. Right? Well, what we can do is a simple analytical trick here. Divide the left-hand side by LT plus 1, but then also multiply it by LT plus 1, right? We're just essentially multiplying the left-hand side by 1. And what do you get? Little KT plus 1 times, what's LT plus 1 divided by LT? Remember, labor supply grows at a constant rate. So LT plus 1 over LT is just 1 plus N. Now, if we subtract both sides of this equation by KT times 1 plus N, you get on the right-hand side S of KT plus 1 minus delta KT minus 1 plus N KT. So then we can write the whole equation as the change in the capital stock from T to T plus 1 times 1 plus N is equal to S F of KT, let's see, plus 1 minus delta minus 1 plus N should be a minus delta plus N KT. Are you guys familiar with this notation, delta kt plus 1? That's the first difference operator of the variable between periods t and t plus 1. This is the fundamental law of motion for capital per worker in the Solow model. It's beautiful, right? Why? Because it characterizes the evolution of capital per worker independent from the rest of the variables in the model. Imagine I gave you the initial capital stock in this economy. So you know what the value, let's say, of K0 is. That's the endowment of capital at the beginning of time. We can use this equation here then to solve for K1, correct? And once we know K1, we plug it back into the right-hand side and it gives us K2. And we can take K2 and get K3. In other words, this law of motion for the capital stock is capable of tracing out an entire history of capital per worker from date 0 on out to infinity. And the shape of that law of motion is determined by the exogenous parameters in the model: the savings rate, the depreciation rate, the population growth rate, the shape of the production function, etc. Right? This is the law of motion for capital in the model. Let me make an important point about a definition here. And I believe this is definition, it might be definition 2 in your notes. And that is the concept of an equilibrium in a macroeconomic model. Now this is a little bit odd because in the Solow model, we don't really have any markets, right? We just assume that there's some endowment of capital and that people save this constant fraction, and so the capital stock accumulates over time. There's no market economy here. Later on in the semester, we're going to talk about economies where people make endogenous savings decisions, and there are competitive markets for goods as well as factors of production. And those markets clear by prices adjusting, okay? In that context, we kind of know what a competitive equilibrium is, and we'll talk more about that. But I do want to draw one distinction here for you at the very beginning of the semester. In the study of macroeconomics, because macro is inherently a dynamic subject, when we talk about the definition of an equilibrium, it is not a static concept, but rather it is an entire sequence of variables that satisfy some equilibrium conditions, okay? For instance, in a Solow model, and this is definition 2, in the basic Solow model without technological progress, an equilibrium path is an entire sequence of variables for capital per worker, output per worker, as well as, I haven't really defined it yet, consumption per worker, lowercase c. So it's not a static object, but it's a dynamic one. So it's a sequence of those variables from date 0 on out to infinity that must satisfy 3 conditions, okay? The first condition is, of course, the law of motion for capital. So given some initial amount of capital, these 3 items, these 3 variables here must satisfy the law of motion for capital. They must also satisfy the production function, right? Once we trace out a whole history of capital stocks, we know what the history of output per worker is. What else must it satisfy? What's consumption per worker in this economy? Agents save and consume a constant fraction of output every period. Savings is constant at S. So what must consumption be in a model without government spending and without an international component? Consumption is just 1 minus S times output, right? Which is just F of KT. So an equilibrium in the Solow model is defined as a sequence of K's, Y's, and C's that satisfy the law of motion for capital, the production function, as well as this identity for consumption where the initial value of capital, let's call it K0, is given. That's actually exogenous, right? The model doesn't tell us what the initial value of capital is. That's an input into the model. Just kind of a rule of thumb here. When you're characterizing an equilibrium in a macro model, you need to have as many equations as you've got variables in your sequence in order for it to be identified, right? We want to trace out the whole history of capital, output, and consumption per worker over time. We need 3 equations to do that. The law of motion for capital, the production function, and this allocation rule for consumption spending.
Could you kind of explain that gamma plus n term?
Gamma plus n. Where do you see gamma?
Or delta plus n by the KT.
This?
All the way at the far right of that.
Well, I'm just combining these two.
Okay.
1 minus delta k minus 1 plus nk, the ones cancel, and you're left with a minus delta minus n.
I just minus what does that
delta.
like kind of mean? Like how is that, like why is delta associated with capital?
Well, it's the depreciation rate,
Okay.
right? So if you start here, right, when you're thinking about the forces that cause the capital stock to move over time, there's really 2 of them. There's the resources you invest in creating new capital, I, but capital wears out at a constant rate. So for instance, capital will grow over time. That is, KT plus 1 minus KT will be positive if investment, that's the amount of corn we plant, exceeds depreciation. That is the amount of corn that rots, right? If investment is lower than depreciation, then the capital stock is going to decline over time, right? So depreciation is an integral component of the process that explains how capital evolves over between periods.
And then why does the population have to do with, like with n, isn't n population?
N is population, but that comes into the intensive form because we've normalized all the variables by L, right? And LT plus 1 over L is 1 plus n. So this is a feature of this discrete time model, right? So I've got to write the left-hand side variable in terms of KT plus 1s, but to do that, I'm going to have this extra LT plus 1 over LT floating around on the left-hand side, which is 1 plus n. And so when and then in this line here, I'm just subtracting KT times 1 plus n from the left-hand side, so I do the same over here, right? And so the change in the capital stock is just basically investment minus depreciation plus population growth. Let me see if I can answer your question a little bit better by talking about a concept called the steady state. And I think that will help the confusion about why population growth is in the analysis. One of the things that we're going to do for every model that we look at in this class is analyze whether or not this dynamic model admits what's called a steady state equilibrium, okay? Now it's a special type of equilibrium that sounds just like the name suggests. It's a point at which the variables in this model settle down into a fixed state, right? K's, Y's, and C's are presumably going to change over time, right? As the economy grows or as the economy shrinks. The question is whether or not these variables will actually slow down and converge to what's called a fixed point in the long run. If we let time run long enough, will eventually get to a point where K no longer changes. In other words, if you put KT on the right-hand side here, it's going to spit out the exact same value for KT plus 1. And if K is fixed from one period to the next, then Y is never going to change. And if K is fixed from one period to the next, then C is never going to change. Does the economy settle down to what's known as a steady state or a fixed point? That is a concept or a position where time gets big enough such that KT is equal to just some K star for all T. These variables that have asterisks or stars are going to designate the steady state long run equilibrium of this dynamic model, okay? It's a stationary point in the model. Well, how can we evaluate whether or not the Solow model admits a steady state equilibrium? Well, these three equations must hold, must be true for every point along the equilibrium path, including in the steady state. So we can simply take the equations of our equilibrium and evaluate them at the economy's steady state equilibrium. All right, so let's do that. Let's evaluate the law of motion here at the steady state. That is the point at which KT becomes K star forever. All right, and so KT is simply equal to KT plus 1 is equal to K star. We've reached that fixed point. Well, let's evaluate equation 1 at that point, okay? What is the left-hand side going to look like? Well, it's K star times 1 plus n, evaluated at time t plus 1, right? Minus K star times 1 plus n is equal to S f of K star minus delta plus n times K star. Now immediately, what do you see is true about the left-hand side here? K star minus K star is just 0, right? So you get S f of K star is simply equal to delta plus n times K star. The left-hand side goes to 0. Therefore, if the Solow model admits a long-run steady state level of capital, what must that steady state satisfy? F of K star divided by K star must be equal to delta plus n over the savings rate. So again, let me emphasize this. If the model admits, and we haven't proved this yet, but if the model actually has a steady state level of capital, it must satisfy this equation. And if that K star exists, then what does that imply about Y star? The steady state value of output. It's just equal to F of K star. And consumption in the steady state would just be equal to 1 minus S times F of K star. We're going to prove, I don't know if I have enough time to do it today, but we're going to prove that in fact the Solow model, with the assumptions that we've made, does in fact exhibit a unique steady state equilibrium. But before we do that, let's look at a graphical depiction of the steady state. And then hopefully this will help clarify why all this junk appears in the law of motion, okay? And by the way, you guys probably, I'm sure you covered this stuff in your intermediate macro. In fact, I know we covered it in principles of macro a long time ago. Okay, so hopefully this will come back. There are 3 forces acting on capital per worker that cause it to go up or down over time. Let's do an informal illustration of the existence of this steady state just graphically, okay? And then hopefully this will jog your memory, because I know we've seen this graph before. It's just been several years. Who did you have for intermediate?
J.
On the horizontal axis, we've got different levels of capital per worker. On the vertical axis, we're going to graph the different components of this law of motion. There's basically two, right? Well, first of all, what does the production function look like? Production function looks like that, right? It's increasing. That is, the marginal product of capital is positive, but it's strictly concave. In other words, F double prime is negative. There's diminishing returns to capital. What does the investment or savings component of this law of motion look like? It's S times F of K, right? Well, S is a constant fraction. So the savings investment schedule is just going to look exactly like the production function. It's just kind of rotated clockwise down a little bit. Kind of like this. In other words, if we pick a value of capital along the horizontal axis and trace up to this schedule, that will tell us how much investment per worker is in period T. Investment is the force that causes the capital stock per worker to rise every period. The more we invest per person, the more capital per worker we'll have the next period. But there's a couple of forces here in the model that cause the capital stock to decline. The most obvious is depreciation, right? But not just depreciation, also population growth. In what sense does population growth, Ben, or anybody, reduce capital per worker over time?
Because it's the denominator, so there's just less capital to go around.
Let's imagine that the capital stock stays constant in our economy. If one of us has babies and we have more people in the economy, we've got the same amount of capital spread over a larger number of people. So capital per worker is going to shrink in the same way as depreciation affects capital per worker. Well, it affects it linearly in the law of motion, right? It's going to look like this. In other words, for a given amount of capital, we can trace up to this depreciation line and over, and that tells us how much capital per worker is going to decline in any given year because of these joint forces of depreciation and population growth. Okay, now let's just pick an initial value of capital. So Jasmine, here's our K0. This is what our creator has endowed us with, okay? According to our little graph here, then we're going to save and invest this much, right? But how much capital is going to deplete because of depreciation and population growth? This much, right? And so what do we see here? Investment is bigger than depreciation plus population growth, what's sometimes referred to as break-even investment in the literature. Therefore, what's going to be happening to the capital stock over time? If investment is bigger than depreciation, capital stock is going to rise. And so next period, K1 is going to be bigger than K0. The capital stock will continue to rise as long as investment exceeds depreciation. At what point will the economy reach a steady state? The point at which investment is exactly equal to depreciation plus population growth. That's where we think the steady state exists. It's the point at which savings and investment is exactly equal to depreciation plus population growth. If we started off with a lot of capital, then depreciation would exceed investment and the capital stock would decline, right? This is kind of an informal illustration of how the Solow model admits this unique steady state equilibrium. It turns out that regardless of where we start, the Solow model is always going to kind of gravitate towards this steady state in the long run. In other words, not only is there a unique steady state, but it is a stable steady state in the long run. That the stability of this equilibrium is actually different than its existence and uniqueness. We'll actually prove both of those things in the course of our discussion of the Solow model. Okay, that makes sense? Let me, when is this class? Is it 4:45? Let me go ahead and start the proof of proposition, I guess it's proposition 1, and we'll conclude it at the start of class on Wednesday.
Did you decide if you need to adjust the time of the class by a few minutes or not?
I made it on time. Okay, so I think I'm gonna, for the time being, I'm just gonna try to keep it to the normal schedule.
Okay.
One thing I may have to do, guys and gal, is if I go slower this semester because of all the technology, I may not be able to cover everything I need to in the hour and 15 minutes. If that's the case, I'm gonna try to make an effort to record what I didn't get through and post it so you guys can watch it. I might announce that, hey, I'm gonna finish the lecture on a Friday and you're welcome to come, but if not, I'll try to post the lecture and just put it on Blackboard for you guys to watch. It's not clear to me that I'm gonna be able to get through everything as quickly as I did in semesters past because of all the stuff that's going on, but we'll cross that bridge when we get there. Okay, so we have come now to, I believe it is proposition 1 in the lecture notes, which says the following: consider the basic Solow model without technological progress, and let assumptions 1 and 2 hold. That is, we're looking at a standard neoclassical production function, Anata Conditions, all that good stuff. If those 2 things hold, then there exists a unique steady state equilibrium where K star is finite and it satisfies this equation over here, and where Y star and C star satisfy these guys. Okay, now what I want to do is a proof of proposition 1. So in your notes throughout the semester, there will be blank spaces in the lecture notes for you guys to kind of fill in these proofs as we go along the way, okay? All right, so K star then satisfies this equation. Let's first verify that K star is indeed a steady state of the model. So if K star satisfies that equation, then it also satisfies the following. S of K star is equal to delta plus n times K star, which means that S f of K star minus delta plus n K star has to be equal to 0. What do we know from the fundamental law of motion for capital? We know that the change in the capital stock between t and t plus 1 times 1 plus n is S times f of kt minus delta plus n times kt. So if we evaluate this equation for kt is equal to k star, what do we get? We get that the change in kt plus 1 times 1 plus n is equal to S f of k star minus delta plus n K star, which is equal to 0. So that means the change in the capital stock is equal to 0. So that implies then that KT plus 1 is indeed equal to KT. So K star that satisfies this equation, or this equation over here, is indeed a steady state of the model. The question is, does that steady state K star actually exist. Part one of this proof is really the existence part. Okay. How are we going to do this? How are we going to prove that a particular finite value of k star actually satisfies this equation? Remember, what's important to remember here is that we haven't made any strict assumptions about f. We've made some assumptions that it satisfies the Anata conditions and that it is a neoclassical production function. But other than that, we haven't parameterized the production function in any way. So how do we know that there's actually a value of k star that satisfies that equation in the first place? Well, what we want to do is look at the behavior of the left-hand side as we move k around. The right-hand side is independent of k, right? So, for instance, what is the limit as, let's say, as k goes to 0 of the ratio f of k to k? What's that limit equal to? Well, as k goes to 0, what happens to f of k? Goes to 0. Capital is an essential input. That's the Anata conditions. The denominator, as k goes to 0, goes to 0. So what do we have here? We have the limit of a ratio 0 over 0. What in the hell do we do then? Come on, you calculus wizards. What do we do? Sorry? L'Hopital's rule, right? This should be equal to the limit as k goes to 0 of f prime of k over 1, right? What's that equal to? What's the limit as k approaches 0 of f prime of k? Anata conditions. The slope of the production function gets very steep as k goes to 0. So the first line here holds because of L'Hopital's rule and assumption 2, the Anata conditions. What is the limit as k goes to infinity of f of k over k? F is strictly increasing in the capital stock. So as capital goes to infinity, what happens to f? It also goes to infinity. So we have an infinity over infinity. And so what do we need to do to evaluate this limit expression? L'Hopital's rule. It's the limit as k goes to infinity of f prime of k over 1. You guys remember L'Hopital's rule from calculus? You just take the limit of the derivative in the numerator over the limit of the derivative in the denominator. Well, what is the limit as k goes to infinity of f prime? 0. And again, we're appealing to the Anata conditions. Okay? Now, let me define for a moment a function g of k as f of k over k. All right? G is continuous for all k positive. How do we know that? Assumption 1 establishes that the production function is continuous, right? And so simple transformation or a function of the production function is also going to be continuous. So this ratio, f over k, is continuous for all positive k's. All right? And we also know that the limit as k goes to 0 of g of k is infinity, and the limit as k goes to infinity of g of k is 0. Can I establish anything by looking at those three observations then? The function g is continuous. It's extremely large for small k, and it's 0 for large k. Therefore, there should exist some k, we'll call it k star, between 0 and infinity, such that g of k is equal to some finite number. That finite number is delta plus n over s. And what theorem am I appealing to in calculus? So boy, can you see this? This is the intermediate value theorem. Right? If you know how the function behaves at 2 points, and you know the function is continuous between those 2 points, then there must be some intermediate point at which that function is equal to, right? Look, let's graph it. Avoy, if I ever forget to move the camera, just shout, okay? Here are my different candidate values for capital per worker. I'm going to graph G on the vertical axis. What do I know? G is really big for K close to 0. G is basically 0 as K goes to infinity. And we know that the function G is continuous. Therefore, there must be some intermediate point here between infinity and 0 where the function G is exactly equal to, in this case, delta plus n over s. That's where the steady state is, by the intermediate value theorem. Now, I don't have time to prove the uniqueness, but the intermediate value theorem does not establish uniqueness. Why? This function G could look like this. Right? What is it that we need to impose on this problem or show exists in this problem in order to establish the uniqueness of the steady state?
Quasi-concavity.
It's got to be what?
Quasi-concavity.
I'm not sure what that means exactly. I've forgotten. We just need to show that G is strictly decreasing, right? If G is decreasing and increasing, then you're going to have multiple steady states. But if we can establish that G is strictly decreasing, we know that that G intersects delta plus n over s only at one point. And that's easy to do, Ben. All we got to do is take the derivative of G with respect to K and prove that it is everywhere negative. And we'll do that at the start of the next class. Okay, Tavoy? I got to go. So I'm a little bit behind schedule already, but hopefully I'll be able to speed up a little bit in the next class. I will talk to the RJ about reserving a room, and then I'll send an email to Nick about what is it, recitation for Friday. And what time did we decide? Was it 11 or 12?
11:45.
11:45 to.
It was like 1.
Okay, so like basically the 12 o'clock to 1 o'clock hour is what works.
11:45 to 12:45.
To 12:45. Okay. Yeah, I'll try to remember to do that tomorrow. All right, and then I'll have Nick send you guys an email. Okay. All right. See you, Tavoy.